performing a tensile test of metal aluminum. This has a width of 11 mm and a thickness of 4.89 mm. And we are performing this test on a strong machine. This machine has two jaws, one is fixed jaw and another is a movable jaw. This jaw is used to load on the metal, and this metal piece is also placed in the center and not any angle. And this is a device that is called extensionometer. This device is used to measure the extension of the metal, and so that's the
Already have the metal piece installed in it, the aluminium piece. Just make sure it is not at any angle to these jaws and it should be in the center. We have extensometer installed in it. We have it attached there. It will just record the measure the length. And here is an emergency button which will turn off the power in any emergency. And also remember, safety is number one priority. So keep on your sunglasses, your safety glasses, and then this machine is connected with that computer, and it has a software Blue Hill. We go for test, and there is a extensometer SI basic tension level 1. It is up to you that which one you wanna use, but it is in SI. And we also have a rectangular sample piece, so we are using SI basic extensometer. And then you go next. You can specify your name. I will give it beta, and beta video project 1, and then go next. Now you can specify the numbers of samples you have. We have only one sample, so we will go with 1. And here you can specify the name so that it will not be tough for you to specify that metal piece in the graph. We have the thickness of the metal, that is 11 point. We have thickness of the metal, that is 4.77, and width of the metal piece, the sample we have is 11.77. And we go next, and then we balance the load on it and reset the gauge so that there is no basic load applied on that metal right now. So then after making it to 0, after making it to 0, we just gonna start.
So we are starting the Instron Blue Hill software, and we are pressing the start button here for tensile testing of the aluminium, and here it goes. And it's beginning to draw the graph in this machine, and the graph is going in this position. This one is the elastic range. That means the material is still in the elastic range. So here the material is getting stretched, and the extensometer is showing the changes. So now the notification has come to remove the extensometer. So we have to remove the extensometer by pressing this, and we have to place it in a good position on the machine. So after this, we have to press the OK once we remove the extensometer, and the plastic region, the elastic region has ended, and the plastic region is started. And now that the material will break, should break because this is in the plastic region, and once the plastic region ends, it will go to the ultimate tensile strength and it will break. So the graph is moving in the elastic region right now. Plastic region right now. The material is stretching. So since the aluminum is a ductile material, it will take more time for it to break, to reach the fracture. Now the thickness is, you can notice the thickness is decreasing and it breaks. Right now the fracture occurs. Now the notification has come to remove the specimen. So we are going to remove the specimen. Once the specimen is not removed, the jaws will come closer and it will damage the machine. So we have to remove that. So the removal is being done now. Once this is done, we have to press OK. Now the jaws are going to its original position, and it's calculating the. It's a graph we obtained from the tensile testing of the material, and this area is called the elastic region. The elastic range is starting from this, from the 0 to this point, and in this region the material will not get deformed. It can regain its shape. This is the elastic range. The structure of, and after that it comes the yield point. This is the point at which the material began to deform plastically, and the point in this stress strain curves at which the plastic deformation, the plastic range starts from here. This is the plastic region, and in this region the material will get plastically deformed. It cannot regain its position back, this is the ultimate tensile strength. This is the highest position, and after that it will start to get to fracture, and this is the fracture point, and after that the material is fractured. Since aluminum is a ductile material, and we use this material only before the elastic range. In this region only it is practically used. This is the plastically deformable stage, and we don't use this much. So this is the tabular representation of the graph, and the specimen name is written aluminum, and the modulus of elasticity is 66,981,327.874 kilopascal, and the load at the yield is 14,106 Newton, and the thickness width we got from the vernier caliper is displayed here, and these are machining specification, and the the strain at the yield point should be 0.2% offset. So that's all clear, and we are going with the modulus of elasticity. This one means this is 66.9 gigapascal. The actual modulus of elasticity of the aluminum material is 69 gigapascal, and we are getting the value of 66.9, and this is producing an error of 2.9%. That's not a big number, but still it's an error. It's caused by the different errors occurring during the testing, and there are the human errors can occur, and the mounting error, that means the slipping between the jaws of the material, and the another one is like a faulty calibration will be causing some errors. That's called the systematic error, and these errors are the result. As a result of this error, we are getting the value of 66.9, and an error percentage of 2.9% error. We should use the material only in the, and this is the elastic region, and when we are using this aluminum material for any practical purpose, we need the material to be in this elastic region. The material beyond the elastic region, that's the plastic region, that means after the yield point, should not be used for any practical purposes. And after the tensile testing of material, we are done with the experiment, and on behalf of all the members of our group Beta, we thank everyone who has helped us in this experiment, especially our lecturer Safa Saleh.
Thank you.
Thank you very much.
My name is Harmit Singh. So now we are supposed to check the hardness for this metal. I think this is aluminium. So this is the Rockwell hardness tester. This is a C scale. So now always first go to the C scale first and check the hardness. So now I'm going to, and yeah, this is the anvil. This is anvil. This is the millimeter from which we will know the hardness, and this is the load to be applied over here. So first of all, just put the as your sample on the anvil and move it until it gets over here. Now we are supposed to make this zero or until here. Yeah, this is done. So now it's on zero. So now just put on the load over here like this. That's it, and wait for the needle to rest. Yeah, you can see the needle moving, so just wait for the needle to be at stationary position. Now, as we can see, the needle has came to its stationary position. Now remove the load from here, like this, and yeah. So now we can see the reading is more than 90, so it means it is a softer material, so we should go for the B scale. Now we have came to the B scale because of the material is softer. So now as you can see, we are supposed to set this needle on zero like this. Move the anvil. Bingo. Yeah, there you go. Yeah. So now you're supposed to put on the load on the sample by pressing this only. That's it. And now you can see it's moving. It's moving. Wait for the needle to be at the stationary position. Then we can and yes, we should not do anything around the tester because it will create vibration and will change the needle's reading. Yeah, just wait for a second. I think it's on. Yeah, it is. No, it's still moving. Yeah. Now the needle has reached to its stationary position. Now remove the load. Yeah, there you go. Yeah, so now we can see now it's good. The reading is almost perfect. It's almost 24 HRB. Let me if we can get the reading on that scale, that would be HRC on C scale. Now we have got the reading on B scale. This is HRB 2024. This is the hardness.
Now we are doing the lab for the sample testing, and in this we have given the two samples. This is this seems to be cylinder in shape and dark green color, and this is cube shape, and this is seems to be light in weight. And in this lab we have we will do the three parts. In the first part we will measure the weight of these two samples. In the second part we will measure the volume by dipping these in the liquid, and then measuring the volume of the overflow liquid. And in the third we will do the check its hardness by using the hardness tester of B scale and the C scale. So in the first part, we are going to measure the hardness, measure the weight of these samples. So this is the sample first. First, we will move the bigger one so as to check that what should be the weight, as it is in between 100 and 200. So we will put it at 100, and then place that the level that is smaller than that on 10, no, 20, 30, 40, 50, 60, 70, 80, 90, 100. So it is in between 90, in between 90 and 100. As we see that the lines are not matching here, so we will move the this most smaller one so that the line should match. No, it is bigger than that. So we will it is bigger than 90. So we will put it at, yeah, this one. Now it is. So it should be more than that. We have to match these two lines. So I think they are matching a little bit less than that. It should be, I think, at 3. Yeah, it is at 3. So the weight is 100 gram plus 90 gram plus 3 grams. That 193 grams. The weight of the first sample is 193 grams. We will note that at the sheet. So this is the second sample. The same way we will measure the weight of this one. So first do it at 0, make it 0. So 100, no, it is in between 0 and 100 grams. So 30 gram, 40 grams, 50, 60, 70, yeah, now it falls. So it is in between 60 and 70, so more than 60. No, it should be less than that. 61. It should be more than 61. More than that. Yeah, I think the line seems to be matched now. It should be later less than that. So it is approximately 60 and 2. It is approximately 62 grams. So this reading also we will note on the sheet. So the next part, my friends will do, that is the volume. They will check the volume by dipping down this samples in the liquid and measuring the volume.
We have to, my name is Gurpreet Singh and this is my user. We have to perform the second step of the metal identification. And this we have the two samples here. But the second step is we have to calculate the volume of these samples. These samples are the irregular shapes. So we have to calculate the sample volume by using the experiment of the flask in which we have to take the samples. Just, Yatin, can you do it?
Yeah. Now to proceed further, we will take the first sample and we'll just hang inside this overflow container. It's a metal overflow container. When we will hang it, the water will just pass out through this nozzle, which we will measure in the measuring flask. So we will just dip in this slowly. So you see then the water is coming out of the nozzle.
Yeah.
That's what we want. Calculate the volume of the object we have got. So I think it's just about it.
We have to just calculate.
So it's done. We will just replace this.
And there is a measuring cylinder flask from where we get the volume of the water. Just we have to put the water here. Now we have to take the reading of the volume, and we got 25 ml.
Yeah, it's around 25 ml.
It's around 25 ml. So for the sample this, we get the 25 ml. Again, we have to repeat the process. We have to first we have to maintain the water so that it cannot come from the nozzle. Just put the water here. Okay, it's okay.
We just need to fill the water up to the brim.
Okay.
So that's fine.
Now we have to take the next sample for this. Can you do this? make sure the thread should be tight so that the sample count can drop it in.
You have to hold the thread firmly so that now again we have to replace this measuring glass. This part of the body is the measuring glass now. See the volume?
What the volume is. Okay, one thing, we have to put it in the level place, then we have to calculate it.
Yeah. Just these are like kinds of human errors which we did.
It's near about 13 ml. So we can, so from this we can calculate the two samples volume, and we can double the both volume of water for the both of the samples. And as we already performed the experiment in our C-scale Rockwell hardness test machine, our reading for that machine the reading should be maximum 65, and but it overcrossed it near about 70. So we have to perform in the B scale. This scale machine is for the softer materials. So we have already set up all the equipment as a procedure. Besides, we have already done it. So we can see that we have to make it the zero reading first. You can see here. Yeah, we have to make it zero, and after that we have to push that knob. Okay, just we have to.
Wait until it's
Yeah, just we have to wait till it don't stop moving. Okay, now we have to push again. It's it's above again 90. So
it is above the C scale in 90, but at the B it is 20.
Okay.
So it is the perfect reading for the this material. It is soft material and its hardness is 20. Its hardness is 20, and that's what we need for this material.
Okay. For this material, we need only now. If the reading is 18B, so the actual accurate rating is 18. So we have already performed this experiment. And from this experiment, we know about that there is a difference between B and C class machine, and that we have this machine is for the softer materials than the C class scale. So we got the reading, and now we can have to perform for the material testing about that the tensile strength. We got tensile strength, we got mass, we got volume. Now we have got to conclusion about the metal samples. Okay, thank you.
My name is Harmeet Singh, and now I'm going to conclude the experiment, which is metal identification using Archimedes principle and by using Rockwell hardness tester. The first sample we tested on was cubical in shape and was shiny silver in color, and its hardness was 24 HRB and volume was 47 milliliter cube, and the mass was 62 grams. So with this reading and taking some reference from the internet, we came up with the conclusion that it was aluminium because it was soft and shiny in colors. It was shiny, that's the virtue of aluminium. And the second metal we tested upon had a mass of 194 gram and was cylindrical in shape and was dark, and it was more like dark gray, and hardness was 27 HRB on B scale, and volume was 13 milliliter cube. So by taking some reference and with the readings, we came up to the conclusion that it was cast iron. So at last, these experiment was very important for us in our practical field, and we will gain much experience from it. And I would like to say thanks to Sheraton College and Dr. Safa Sadeh for guiding us through the whole procedure.